is centroid. Okay? The first moment of area cannot cross over the centroid, i.e., the shaded region that you see, right? This shaded region that you see, the maximum that can go is where y is equal to 0. Okay, so it's this entire area. You cannot take first moment of area. We cannot do first moment of area like this. Okay, we cannot do first moment of area. Okay, doing simple analysis, we cannot take first moment of area doing this. Okay, so let's say this is the point of interest. Let's say we call it point A. You cannot take your first moment of area to cross the centroid. Okay, so this is what? This is wrong. Okay, it cannot cross the what? It cannot cross the centroid. And then for now, rule number 5 is that Q, or the shear flow, can only flow in one direction. So i.e., if I were to construct our shear flow, it will look like this. Okay, it will look like this. So this is Q, this is Q, and this is Q. And if you look at shear flow, right, the word flow is very similar to liquid flow, right? The flow of liquid from top to bottom. Okay. Now let's do a short example, or I want you all to apply what these 5, or apply these 5 rules. Okay. So let's go through it again. Okay. So rule number 1, right? Rule number 1, V and I are constant. Rule number 2, geometric datum is always at the geometric centroid. Rule number 3 is that the analysis starts from the distance furthest away from the centroid. Rule number 4, first moment of area cannot cross over the centroid. And rule number 5, the shear flow Q can only flow in one direction. Okay, so let's do a very simple, okay, example, okay, where you don't require any calculation. Okay, let's do this one. So now we have a structure like this. Okay, so now we have a structure like this. Hold on, my apologies. Okay, now we have a structure like this. So for example, now if we want to find, okay, so I'll draw for you where the geometric centroid first. Okay, so this is where our geometric centroid is, and our geometric centroid correspond to our, okay, so this is our geometric centroid. And this corresponds to our datum. Okay, so this is the datum. So now I'm going to define a point over here. Okay, so down here now, I'm going to call a point, and I'm going to call this point just call I. Okay, so this point that I've just drawn is I. Okay, so we are going to find the shear stress. So V XY at point I. Sorry, VXY, come on, UG. Shear XY at point I. So the formula we're going to apply is Vy, which is a constant, over Izz, which is a constant. The problem now is this. What is Qz and what is your T? Okay, what is the Qz and what is the T value. Okay. So now, so we have to find the QZ. Okay. So I know now, okay, and it's pretty straightforward. The area of interest now is this. Because I is over there, this is our area of interest. Where the blue line, I'm drawing the blue line. There's the area of interest now. Okay. And then the first moment of area, right, is this area over here. I'm shading now. Okay. So this is pretty straightforward because we know that Vy is coming from the top. Right? Right. That is the area that we are interested in. Okay. So for this case, right, we know that QZ, right? We know that QZ is equal to A Y bar. Okay. So now if I were to calculate the area, right? So the area, I just going to put in numbers. The area is the width is 0.16. Okay, 0.16. And the depth, for example, now my depth from here to here is about 10 millimeters. Just an example. So the depth is equal to 0.01, right? And then you have the Y bar. So Y bar is basically this distance, okay? So this over here, this distance over here is your wait, that, okay, that distance over there, let me try to, so this is our Y. Okay, so we want to find our Y bar. So if you were to ask me to draw my Y bar or our Y bar, this is the distance of the Y bar. Okay, so this is our Y bar. Okay, so that distance over there, the Y bar over there, as you can see, will be equal to Y plus by 0.01 divided by 2. Okay. Okay, because the entire thickness is 10, and the defined area centroid is 0.01 divided by 2. Okay, so the thickness over here now, which is pretty straightforward, the thickness now over here is equal to 0.16 meters. Okay, straightforward. Anyone, any doubt? Okay, so that is how we find the shear XY at point I. Okay, Vy over Izz are constant, so don't worry about them. It's the QZ and T that will change. Okay, let's do another same figure. Okay, I'm going to do the same figure. If I may. Okay. Did not work. Now, our area of interest change. Okay. Now, okay, so for this case, we now want to find, okay, the shear XY at point A now. Okay, we want to find shear XY at point A. Okay, so this again, the formula is Vy over Izz QZ divided by T. Okay. Now, so the area, the defined area now, because it's at point A, the defined area that we want to look for is this whole area now. And why is that case? Because this is the what? analysis direction. The analysis will start from where? Y max, yes or no? So this is the analysis direction. That's why we look at this distance over here. The analysis starts from Y max, right? Then it comes in. So that is our analysis direction. So for this case, the first moment of area is easy. Okay, not easy, but it's equal to QZ. We know that the width is equal to 0.16. The depth is equal to 0.02. And then the Y bar, pardon me, I better write the formula. So A multiplied by Y bar. So first moment of area about the z-axis. So the width is equal to 0.16. The depth is 0.02. The Y bar is Y plus by, or Y, what did I call it before? The distance. So it's Y. Okay, so from the distance from here to here is Y plus by 0.02 divided by 2. Okay. Now, which thickness will we take? As you can see, at point A, right? At point A, the thickness T can be equal to 0.16 meters, or T is equal to twice of 0.02, which is equal to 0.04 meters. Right? So there are two possibilities. There are two thickness. Which one will you take? The bigger value or the smaller value? The answer is to use the what? Use the smaller thickness. Okay, to get the higher shear stress. Okay, higher shear stress. Or higher shearing stresses. Okay, there's no point using 0.16 because if Vy, Izz, Qz are constant, and T, if you use a bigger number, the shear stress is smaller. If you use the smaller thickness, your shear stress is bigger. Now, at point A, you have to put the 2 down here because you have a what? You have the left thickness, okay, left thickness, and then you have the right thickness. Okay, so this is still pretty straightforward. Nothing difficult. We have been obeying all the rules. What are the rules we apply? Obey. The rules were the 3 rules we apply is the geometric datum is at the centroid, right? The analysis start from Y max. That's a rule number 2. And then did we apply rule number? Wait. V and I are constant. Okay. Now, let's see this case now. Okay. So now, if we were to do this now, then I'll try to, I wonder, does this work? Yes. Okay. Now the next question is this. We'll get rid of this. We are going to determine now that the shear XY at point B. Point B is of interest now. Okay. And we know, right, for non-thin wall, we know that the formula we're going to use is Vy over Izz. These two are constant. Now, what is the Qz and what is the T? The T is easy. The T we know is twice multiplied by 0.02, right? Which is equal to 0.04 meters. The problem now is how to determine the Qz. So as you can see, there are two possibilities. Okay, there are two possibilities. Let me tell you what are the two possibilities.